knowing all of that, if we know that the normal model is appropriate, we can use all of the math we have about normal model probability and distributions to answer some important questions. Because we're going to be talking about the normal model, let's refresh ourselves on that 68, 95, 99.7 rule. So in this case, let's say I know that I have a distribution where the mean is 0.25. Okay, so let's give it to me right here. And I know that the standard deviation is 0.04. So this is just refresher. Then if I go out 1, 2, 3 standard deviations and minus 1, 2, 3 standard deviations, I get almost all of the information. So adding 0.04, I get 0.29, 0.33, and 0.37. Subtracting 0.04, I get 0.21, 0.17, and 0.13. So remember, 68% of the data lies in here between the first, the mean minus 1 standard deviation and the mean plus 1 standard deviation. So I can say that 68% of the data will be between 0.21 and 0.29. Then if I go out 2 standard deviations on either side, I get 95% of the data. So that's going to be between 0.17 and 0.33. And if I go all the way out to minus 3 standard deviations, all the way to plus 3 standard deviations, that's almost everything. That's 99.7% of the data. So 99.7% of the data will be between 0.13 and 0.37. Now, in order to use the normal model in these specific problems, we need to meet some conditions. So condition number 1 is that we need our sample to be random and independent. So we talked about how we do a simple random sample, and we talked about possible sources of bias. So this only works if our sample is random and our samples are independent from each other. Condition number 2 is that we need to have a big enough sample. So we need to have at least 10 successes and at least 10 failures. Now we can check for that proportion-wise because the successes are going to be n times the probability of success. So n times p needs to be bigger than or equal to 10. And for failures, we need n times 1 minus p to be greater than or equal to 10. So that'll give us at least 10 successes, at least 10 failures, and should be big enough for the math to work here. Condition number 3 is that we need a big population too. If the sample collected is too big, things can sort of happen in a misbehaved way. So the way we say this is that the population size has to be at least 10 times bigger than the sample size. Sometimes you also see this put as the minimum population we need has to be the sample times 10. Okay, so that's just moving the 10% onto the other side of this equation. So another way of writing this is that the sample has to be less than or equal to 10% of the population size. Those are giving us the same pieces of information. Now we're going to use this to do an example. So here's our voting example. In a large population, 35% of people plan on voting for Measure K. A sample of 100 adults is taken. What proportion do we expect will vote for Measure K in our sample? What standard deviation do we expect? So the first part of this, when we say, what proportion do we expect will vote for Measure K? It should not be any different than for the whole population. So we expect that P hat is going to be the same as P is going to be that 0.35%. Okay. Now the standard deviation is where things get more interested because here we need to calculate our standard error and it depends on how big that sample was. So our standard error in this case is the square root of p, that's 0.35, times 1 minus p, which is 0.65, divided by the sample size, divided by n, which is 100. And when we do this, we get something like 0.047. Now, if I was doing a homework problem that was asking for this, I would keep it as 0.47. I might even have more decimals, but in this case, I'm actually going to round that to 0.05, and you'll see why in a second. Now that I have that, remember that this is like my standard deviation, and this is like my mean. So with those two things, I can build a distribution curve. So if I think about what's going to happen with this sample, well, probably it should be about 0.35, but it might be a little bit bigger, and it might be a little bit smaller. And the standard error says, hey, if I go out 1, 2, 3 standard errors on this side, minus 1, 2, 3 standard errors on this side, I'll basically capture everything that can happen. So adding that 0.05, I get 0.4, 0.45, and 0.55. Subtracting that 0.05, I get 0.3, 0.25, and 0.2. So this graph is telling me that 99.7% of samples are going to be between 0.2 and 0.55. So almost everything should be in that 0.2 to 0.55 range. If somebody takes a sample and it's outside of that, if they get to take a sample and it's 0.75, I'm going to think maybe there's bias, maybe something didn't work with the conditions. I can also say that 95% of samples are going to be between 0.25 and 0.45. Oh, I think I made a mistake here. I think this should have been 0.50. So this should be 0.5. There we go. And we can do the same thing for 68%. So this lets us quantify what's a normal sample and what's sort of an abnormal sample.